Good afternoon, everybody. We don't have that many with us, but hopefully we've got more joining. Try to give a few minutes of grace, but we need to get started. So we're starting with the tail end of Chapter 10. We covered most of it last week. We'll finish up Chapter 10, and then we'll do some practice problems to make sure that you get it. Then we'll do some Chapter 9 homework problems that I saw folks had some trouble with. That's the game plan for today. My last class, they finished early. So you might finish early too. We'll see. But we can use the time afterwards as office hours, or if you just want to go, then you're free to go. So let's get to it. We left off talking about the kinetic molecular theory of gases. So we talked about collecting wet gas, we talked about partial pressures. Now we're talking a little bit more about gases themselves, how they move, and how temperature and energy are related. For this slide, you'll need to know these different points, and the type of question would be like a multiple choice question, which one of these is part of the kinetic molecular theory or something like that. So here we go. Gases are made up of tiny molecules. We already know that. There's a lot of empty space between the molecules. Gases are very low density. We know that just from the properties of gases. Gas molecules demonstrate rapid motion. They move really, really quickly in straight lines, and they travel in random directions. These molecules have no attraction for one another, which also means they don't repel each other either. They see each other, but they keep going. When they collide, they don't lose any energy. So it's just kind of like a bounce house, when you jump, bam, jump up, go back down. You just bounce off of each other. Or bumper cars, when you're driving around and you just kind of bump into someone. I apologize, that's my son trying to make an appearance on the last day of class. It's like bumper cars. When you're driving around, you bump into someone, you just kind of bounce off of them, and you keep going. The average energy that a gas molecule has is related to the Kelvin temperature. So we've been doing all of our operations with Kelvin temperature. The reason is because the kinetic energy is related to the Kelvin temperature, not Celsius. So again, know these, understand them in terms of being able to answer like a multiple choice question. So are we good here? Let me know if you need more time on this slide to write it down. Don't everybody answer at once. Okay. Thank you, Whitney. So we've got one more concept that's kind of related to the kinetic molecular theory, and that's absolute zero. When the temperature where pressure and volume of a gas theoretically reaches zero is absolute zero. And on the graph, that's here. Now we haven't gotten there yet experimentally to be able to reach absolute zero. We've gotten pretty close, but we haven't reached absolute zero. When you extrapolate that back and you're looking at the temperature in Celsius, that's negative 273 degrees Celsius or 0 Kelvin. So keep that idea in the back of your head. The concept of absolute zero. The temperature where the pressure and volume of a gas would theoretically be 0. Questions here, or are we good to move on? Okay. The final gas law that we need to introduce is the ideal gas law. The other gas laws, we didn't take into consideration the amount of gas. The ideal gas law does. So part of the equation here, we've got P for pressure, V for volume, T for temperature. We've seen all those before. N is going to be the number of moles of gas. And R is the ideal gas constant. This value will be provided for you for the exam and is 0.0821 liter atmospheres per mole Kelvin. This is just a number that when you take into account how the pressure is related to volume, temperature, and moles, this constant makes it so that we can say equal to versus proportional to. That's all you need to know about that. There are other R values for different units of pressure. So this one is for atmospheres. You can look it up on Google, but for the purposes of our class, when you have a pressure that is not an atmosphere, I want you to convert that pressure to atmosphere. I'll show you what I mean when we're doing some practice problems. Does everybody have the ideal gas law copied down? So we're going to do some examples next. Okay. So let's move on. We'll start with a simple problem. How many moles of neon gas occupy 2.34 liters at STP? You're not going to have the luxury of seeing, oh, this is an ideal gas law problem. Let me use the ideal gas law. So we have to learn how to recognize it from reading the problem. If we're talking about gases and the number of moles, anything that indicates amount of gas, that's going to lead you to use the ideal gas law. And just like with the other gas laws, you'll want to assign all the variables that you have and figure out which one you're solving for. We're given a volume of 2.34 liters, and it says at STP. That's standard temperature and pressure. Does anybody remember what that means in terms of what the temperature is and what the pressure is? We talked about this in chapter 8, about what STP stands for. If you know it, you can throw it in the chat. So 22.4, that's the molar volume, right? And that is absolutely related. So at one mole of gas has a volume of 22.4 liters at STP. But the conditions for STP are 273 Kelvin and 1 atmosphere. You will need to know that. Okay? Yeah. So make sure you know that. I can say that something is at STP, and that gives you the pressure and the temperature. R is a constant, and the number of moles we don't know. So the next part in this is to rearrange the ideal gas law to solve for the number of moles. To do that, you divide both sides by RT. Then you substitute in your variables. Put that into your calculator and let me know what you get in the chat. In this case, we need 3 significant figures because of our volume. But that's pretty close. So 0.104 moles of gas. So that's a simple application of the ideal gas law. Are there any questions here? I have a little bit more complicated question coming up next. So if this one's a struggle, we're not ready for the next one. So let me know if you're ready. Okay, then let's go. What volume in liters is occupied by 3.38 times 10 to the 22nd nitrogen molecules at 100 degrees Celsius and 255 millimeters of mercury? This is another ideal gas law problem, but instead of having a number of moles, we have a number of molecules. How do we get from the number of molecules to moles? Does anybody remember what that's called? The number? This is from chapter 8. Right. Avogadro's number. So in 1 mole, you have 6.02 times 10 to the 23rd molecules. That's hint number 1. Hint number 2. Your pressure is 255 millimeters of mercury. That's not atmosphere. So you need to convert that to atmospheres. There are 760 millimeters of mercury in 1 atmosphere. The final hint I'll give you before I let you loose. Our temperature is in degrees Celsius. We need Kelvin. You need to add 273 to your degrees Celsius temperature to get Kelvin. Those are all the hints I'm going to give you. I want you to try this problem on your own. I'll give you 3 minutes, and then I'll check back in. If you don't have an answer yet, that's okay. I'll start working it out. We said this is an ideal gas law problem. So we're going to use the ideal gas law. This time, we're looking for a volume in liters. So we need to rearrange the ideal gas law to solve for volume. Divide by the pressure on both sides. And you can get the volume. Now let's go through and do all these calculations that I gave hints for. For your N, the number of moles, we have to take that 3.38 times 10 to the 22nd molecules and use a unit factor using Avogadro's number. Are we going to put Avogadro's number on the top or the bottom of the unit factor? We're going to put it on the bottom. When you do that math, you should get a fairly small number. So that's our N. Now let's deal with that pressure. We have 255 millimeters of mercury. We need to convert to atmospheres. So we'll put atmosphere on top and 760 millimeters of mercury on the bottom. So we should get 0.3355 atmosphere. We're not worrying about rounding yet. We're not at the end of the problem. Finally, with our temperature, we have 100 degrees Celsius. We need to add 273 to that for Kelvin. So that's 373 Kelvin. Now I'm going to box all of the information we have so far. We've got our temperature. We've got our moles, which is our N. We have our pressure. And we know R. Has anyone gotten an answer yet? Do you want to share before I do the reveal? It's okay if you don't want to share. All right, thanks for sharing, Patrick. So I'm writing it all out now. Now, if you did some rounding with the number of moles or with the number of with the pressure, then you might get something a little bit different. But for the final answer, I got 5.12 liters. So you were definitely in the right ballpark. I think it may have just been a rounding thing, Patrick. How's this question feel? Does it make sense, all the steps we had to go through? We can re-go over it, or you can let me know if you're ready to do some more practice problems. So we ready for practice problems then? Okay, I can wait. We had to convert the pressure because the gas constant that we're using is liter atmosphere per mole Kelvin. So the constant only works if your pressure is in atmosphere. So just like with the volume, it has to be in liters, not milliliters or anything else. So we'll see that these gas laws, the ideal gas law is the most particular in terms of units. All the other ones, it doesn't really matter as long as you use the same units. But for the ideal gas law, because there's a gas constant that has units attached to it, all of the pressures and volumes and temperatures have to match the units in the gas constant. Does that help, Whitney? Okay, good. All right, then let's go. Now we're just going to do some generic practice problems. This is going to pull from all of Chapter 10, so all of the gas laws are fair game. I'll give you a minute to read it through and search through your notes, and then I'll start solving the problem. So in this case, we've got a deep sea scuba tank that has oxygen and helium. If the partial pressure of the gases are 3,300 millimeters of mercury and 125 atmospheres, what's the total pressure in atmospheres? I'll give you 3 minutes to read the problem and get started. Then I'll chime in and start solving it. But let me know if you get stuck before that, and I can help you out. I'll go ahead and start solving the problem here. So this is talking about partial pressures. We're going to reference the Dalton's law of partial pressures. And what that says is that the total pressure is equal to all the pressures of all the gases in the container. Just add them up. That's the law of partial pressures. Here, we've got two gases. We've got oxygen and helium. But we can't just add them straight up because we've got millimeters of mercury and atmospheres. The question is asking for the total pressure in atmospheres, so it makes more sense to take the 3,300 millimeters of mercury and convert that to atmospheres before we try to add. So that's the key to this problem, realizing that you've got two different units that you need to do something with. So we've got our 3,300 millimeters of mercury. We need to write a unit factor that's going to convert that to atmospheres. What's our unit factor for this? Yes, 1 atmosphere over 760 millimeters of mercury. When you do that math, you'll get somewhere in the ballpark of 4.3. There's a bunch of other numbers after that. Now we can add these two together. We're going to go with, we've got two significant figures in the 3,300 millimeters of mercury and 3 sig figs in the atmospheres for the helium. So we have to go with 2 sig figs here. Since we did 2 different operations. So does that make sense? I think it was this class that we were talking about doing an example of the partial pressures where you had 2 pressures that have 2 different units. So this was the practice I was talking about. Does this make sense for everybody? We're still pretty light on the number of people in class today. Anybody know what's going on? It's our last class. So if you know somebody isn't in class, and they should be, text them, bother them, say, hey, come be with us. Learning is fun. All right, next problem. The decomposition of baking soda produces carbon dioxide gas. If 42.5 milliliters of wet gas is collected over water at 25 degrees Celsius and 764 millimeters of mercury, what is the volume of dry gas at STP conditions? And you're told that the vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury. This is a big paragraph of information. There's a lot of numbers here. So I'm going to help you sort through it a little bit, and then I'll let you loose on the problem. We see the term wet gas. Remember, wet gas means your gas sample plus water vapor. So if we're looking at a total pressure, it's going to be the partial pressure of the gas plus the partial pressure of the water vapor. The first step is to find the pressure of your gas using Dalton's law. The second step, we're using a different gas law. So if we look at the information we have a volume, 42.5 milliliters. The pressure, we're going to find that. That's the P gas from before. And we have a temperature of 25 degrees Celsius. We're asked about the new volume at STP. Well, we know that standard temperature and pressure means 1 atmosphere, and it also means 273 Kelvin. What gas law can we use that takes into account pressure, volume, and temperature? Take a second and look at your notes and tell me which one you might use. Yes, the combined gas law. So there's your hints. Try to solve this problem. I'll give you 3 minutes head start, and then I'll chime in with the answer. All right, I'll start solving the problem. You can feel free to put your answer in the chat if you want to, or you can just wait until I get to the final answer. So for the first part, we're going to use the total pressure, which is 764 millimeters of mercury. And we're going to subtract the water vapor. This is the pressure of our carbon dioxide gas. Next, we have to use the combined gas law. Before we use it, we want to cross multiply to make our lives a bit easier. This time we're solving for V2. And we're going to divide both sides by P2 and T1. That's the equation that you should use to solve for V2. Then we just have to substitute in all of the information we have. So the initial volume is 42.5 milliliters. P1 is what we just solved for part 1 with the partial pressures. That's 740.2 millimeters of mercury. P2 is 1 atmosphere, that's STP, right? That's the same thing as saying 760 millimeters of mercury. Then T2, STP, that's 273 Kelvin. And our T1 is 25 degrees Celsius. That's 298 Kelvin. When you do all that math, you should get 37.9 milliliters. And one thing you'll want to be careful of, depending on what calculator you use parentheses here for your pressure and your temperature to make sure that you get that division done before the multiplication. So how did this work out for everybody? Did we get the answer? If you didn't get the answer, do you understand why you didn't? Sure, I can walk through this one again. So this is definitely one of the more complex ones because there's a lot of numbers involved. So let's start with reading the problem and breaking that down, because I think that's the crucial part here. So we've got baking soda that produces carbon dioxide gas when it decomposes. We collect wet gas over water at 25 degrees Celsius and a pressure of 764 millimeters of mercury. The question is asking about the dry gas at STP conditions. So we have to do something to figure out the partial pressure of the carbon dioxide gas. Remember that wet gas is the gas plus the water vapor. If we're told what the total pressure is, that we're collecting all of this gas and this is the total pressure, we can use that chart that I showed you the last week that has the temperatures for water and the vapor pressure at each of those temperatures. So I did that for you. You use the partial pressures to figure out what your pressure of carbon dioxide is. So does this first step make sense? The total pressure is 764. We subtract off the water vapor. We get the pressure from the carbon dioxide gas. Does that part make sense? Okay. So no, Whitney, we subtract the water vapor because we don't care about the water. We care about the dry gas sample that we want, which is the carbon dioxide gas. Whenever you collect a gas over water, some of the vapor is going to be water vapor. We just want to know the pressure from our gas sample, not the water. And when we're doing the next step, where we're calculating what the volume of the dry gas is at STP, we don't want to calculate anything that has to do with the water vapor. We want dry gas, which means no water. Is that clearer? Okay. Yes. Yes. So we keep the volume and the temperature because that applies to both the carbon dioxide gas and the water vapor. The only thing we had to separate out was the pressure, the partial pressure of the carbon dioxide away from the vapor pressure of the water. Yeah, they both contribute to the total pressure of 764 millimeters of mercury. Okay? Yeah. So now that we've got that straight, you can look at the variables you have: pressure, temperature, and volume. The only gas law we have that just deals with those is the combined gas law. So you can use that and rearrange to solve for the final volume and put in your numbers. So I know you can do that part. The trickiest part is reading the question. So you see how I wrote my plan here? I recommend that you write a plan too, because all the questions you get for the gas laws are not going to be straightforward. This is Boyle's law. This is Charles's law. You're going to have to combine some concepts. I posted already chapter 10 practice problems and the answer key. So I would definitely recommend going through those and pull on up to office hours tomorrow if you have questions. I'll also have some office hours the week before finals. So if you have any questions then, you'll be able to pop in then too. So are we good to move on? Yes, I will not leave you hanging between now and finals. Okay. Next question. We've got a sample of fluorine gas and it occupies 855 milliliters at 710 millimeters of mercury and 255 degrees Celsius. We need to figure out what the mass of the sample is. Anytime we're dealing with mass, that means we're trying to figure out the number of grams. The only gas law that we have that's even remotely related to the mass of a sample is the ideal gas law. And the reason why it's related is because we can figure out N, the number of moles. So for this problem, the first step is to use the ideal gas law to solve for n. And then you need to convert moles to mass. This is another chapter 8 throwback. What do we use to go from moles to mass or mass to moles? It's got mass in the name. Molar mass. The other thing you need to know, fluorine gas. Fluorine gas is a diatomic molecule. So that means its chemical formula is F2. When you're calculating that molar mass, it's going to be fluorine times 2. Other hints that I'll give you that I want you to pay attention to. 855 milliliters is your volume. But you need that to be in liters. You also have 710 millimeters of mercury. That needs to be in atmospheres. And last but not least, you've got a temperature in degrees Celsius. That should be Kelvin. So you've got some conversions to do before you can use the ideal gas law. Don't just throw the numbers in. Make sure that your units match the gas constant. And that's liters, atmospheres, moles, and Kelvin. I'll let you loose on this problem. I'll give you until 3 o'clock, so that's like 4 minutes. And then I'll check back in. So I'm going to start writing everything out here, because it's going to take me a minute. But you can keep on working, and you can put your answer in the chat if you want to. There aren't that many of us, so it's a small family today. Hopefully you feel comfortable sharing. And if you're stuck or you're like, I didn't get it, you can let me know that too, as always. Ain't no shade. It's okay. So let's do all these variables. I'm feeling a little colorful today, so let's do something different. So we've got 855 milliliters as our volume. That needs to be in liters. Divide by 1,000, and that gives you 0.855 liters. Our pressure is 710 millimeters of mercury. Divide by 760 millimeters of mercury, and that will give you the pressure in atmospheres. Then our temperature is 255 degrees Celsius. Add 273 to that for our temperature in Kelvin. And of course, R we already know. I'll rewrite it down here. So we're going to solve for N. Yeah, so N, I think you may have missed a 0 there. So it should be small. So that's our N. Now you're good. Now we need to use that with the molar mass. The molar mass of fluorine gas is about 38 grams per mole. Your calculator is going to say something like this. I think I put too many 9s there. We only need 3 sig figs. So that's our final answer, 0.700 grams. You'll absolutely see a question like this on the exam. The last one too. So giving you these practice problems, it's giving you an idea of the types of problems that you're going to see on your final exam. Because remember, there's no exam 5. It's just going to be the final. And the final is going to be like, kind of like an exam on 9 and 10, plus some throwback questions from the other chapters. Does this one make sense? Do we need to go through it again? Let me know. Yes, the last one had a lot of numbers in it. Okay. Then we'll keep pushing forward. I'll leave you with an easier one. This is the last gas law problem, and then we'll move on to a few of the homework problems. So you've got a sample of argon gas with a volume of 125 milliliters. The pressure changes from 705 torr to 385 torr. If the temperature remains constant, what's the final volume in liters? So we've got pressures and volumes. What gas law should we use for this? We have pressures and volumes. Which gas law should we use to solve this problem? Yep, this is Boyle's law. Notice that the question is asking for the final volume in liters. Our initial volume is in milliliters. When you rearrange, you get something like that. And then you throw in your numbers. You should get something in the ballpark of 0.229 liters. So I just went through that one because it was pretty easy, pretty straightforward. But let me know if it wasn't easy or straightforward for you. Alright, if we're all good, then we have a decision to make. The next few problems are problems from the homework. We can take a break and then get back to it, or we can go straight through and you'll have time to spare for sure, because we're not going to take up a whole nother hour and change with going over 4 problems. So let me know if you just want to keep going or if you want to take like a 15-minute break now. All right. Then we're going to keep going. So chapter 9 review. I looked over the mastering chemistry to see where people were struggling. And I pulled some of those questions just so I can give you some help, illuminate some things for you. The first one I pulled was the one about the electric current passing through water. So when that happens, you liberate hydrogen and oxygen gas. The question is asking what's the STP volume of oxygen gas obtained from the electrolysis of 90 milliliters of water. The first thing you have to do for this problem is write a balanced equation. You're not given one, but you're told what the equation is, and then you just have to balance it. You've got liquid water. There's some kind of a current passing through it, and you're making hydrogen gas and oxygen gas. This is not balanced. When you balance the equation, you should end up with a 2 in front of both the water and in front of the hydrogen gas. So unless y'all want me to, I won't go through how to balance it. So do you want me to, can I keep going, or do you need me to show you how to balance it? Okay. Then let me erase this and I'll show you how to do it. We've only got 2 elements here, hydrogen and oxygen. On the reactant side, there's 2 hydrogens and 1 oxygen. On the product side, there's 2 of each. We have to start somewhere, so let's start with the oxygen, since that's the one that looks like it is unbalanced. We're going to multiply by 2, because the lowest common denominator between them is 2. And that means putting a 2 in front of the water. Then we take stock of what we have again. Now we've got 4 hydrogens and 2 oxygens on the reactant side. 2 hydrogens and 2 oxygens on the product side. Now we've got a problem with the hydrogen. The lowest common denominator between them is 2. So we're going to add a 2 in front of the hydrogen gas on the product side. We'll do one more table just to do our final check, but this should be balanced at this point. We've got 4 hydrogens and 2 oxygens on the reactant side, 4 and 2 on the product side. So we've got a balanced equation. That's step 1. Step 2 is recognizing that 90 milliliters of water is the same as saying 90 grams, and here's why. The density of water is 1 gram per milliliter. So if you have 1 milliliter of water, it weighs 1 gram. If you have 90 milliliters of water, it weighs 90 grams. Now we can assign the type of problem. We've got a mass of water, and we're trying to get to the volume, which is liters, of oxygen gas. This is a mass to volume question. For that, we start with the mass of water. We use the molar mass of water to get to moles of water. From there, we have to get to moles of oxygen gas. You have to use a mole-mole ratio to get there. And it's going to be the oxygen gas over water. That's the form that it's going to have to be in. Last, we need to get from moles to liters. That's molar volume. 1 mole of gas is equal to 22.4 liters. We're at STP, so that's why we can use molar volume here. Is everybody with me so far? Now we just got to fill everything in. The molar mass of water is just a bit over 18. Oops. I'm supposed to be using different colors. So that's the molar mass, and that'll get us to moles of water. Now we've got to do the mole-mole ratio, and we're going to go to our balanced equation to look at the coefficients. In front of the oxygen, we don't see a coefficient. That means it's 1. In front of the water, there's a 2. We write that as 2 moles. And that's our mole-mole ratio. Third, we're taking the moles of oxygen gas and converting to volume. Put the 22.4 liters on top and the moles on the bottom. Make sure everything matches up. So we should end up with liters. And that's what you would get. So I just pulled 90 out of a hat. I don't know if anyone had 90 milliliters of water, but it's the same process for this question regardless of what amount of water you have. So does this make more sense? Are we ready to move to the next problem? All right. The next one I pulled out was a mass to mass problem. So I know one of my classes had issues with this. Did you guys have an issue with this one? This was another one where you had to balance the equation first. You were given an equation this time, but it was unbalanced. So let me know if you want me to go over this one, or if you were okay with this. Yeah. So what's the consensus? Do we want to go over this one? Okay. So I'll put it, I'll try to put the answer to it in the notes before I post it online, but we don't have to go through it. So I actually put 2 slides in because I didn't have enough room last time. This was another one of those where you had to balance the equation first, but this one may have been a little bit more difficult to balance. This is a combustion reaction. Once you get the balanced equation, it's much easier to do the problem. So I'll show you how to balance this one. This is one of the ones where you have to use a fraction. We've only got 3 elements: carbon, hydrogen, and oxygen. Reactant side, we fill in what we have. Product side, we fill in what we have. For the oxygen, you see oxygen in 2 places. There's 2 in the carbon dioxide, 1 in the water, for a total of 3 oxygen atoms. That's going to be the hardest part to balance because you see it in 2 places. So we'll start with simply balancing the hydrogen. We'll go ahead and add a 5 in front of the water. We didn't do anything to the reactant side, so I'm just going to copy that down. The product side, we changed the hydrogen and the oxygen. So now the oxygen is 2 from the carbon dioxide plus 5 from the water, which is 7. Next, we'll focus on the carbon. We're going to multiply by 4 on the product side. Again, we have not touched the reactant side, so we'll leave that alone. We did touch the carbon dioxide, which affects the carbon and the oxygen. Now we've got 4 times 2, which is 8, plus the 5 oxygen atoms from the water. That gives us 13. Now you might be looking at yourself like, okay, 13 and 2. That doesn't go together. However, in this case, what you have to do is use a fraction. We need 13 oxygen atoms. Each molecule of oxygen gas gives us 2 oxygen atoms. So if I want 13 of them, I have to write a fraction. 13 over 2. And that would give me 13 oxygen atoms. We can't leave it like this because that's bad form. So what you have to do is multiply everything by 2. So your final answer, and this is just for balancing, that's your final answer. And you can do a chart to show that that's what the answer is for the balancing. And I'll throw that up here real quick. Oops, I wrote 26 instead of 13. I knew something was wrong. There. So for the number of oxygens on the product side, you've got 16, which is the 8 times 2 from the carbon dioxide, plus 10 times 1, that's 10, for a total of 26. That's the balanced equation. Now, you can go ahead and say, if you have 2 moles of water, how many moles of butane gas react? Well, our butane, we've got 2 moles. And the water, we've got 5. So 2 over 5, that's 0.4. And 0.4 times 2 gives you 0.8. So that was definitely a little bit of a challenge problem when it comes to balancing. But hopefully that made your life a little bit easier. I'm not going to do that to you on the final exam. But did that help at least understand where you went wrong? Okay. Well, I managed to fit it all on here. So I duplicated the slide just in case I needed the space. That's it, y'all. You have Mastering Chemistry homework and quiz for Chapter 10 due on Sunday. There's no chapter check-in. Don't forget that I have office hours tomorrow from 2 to 4. So if you need help with anything, just want to stop by, you're more than welcome to. Next week, no class, no office hours, because it's gobble gobble. So when you're traveling home, be safe. Enjoy your family, enjoy your friends, but be safe. And we will have office hours. I'll set up a day the week before finals. I was talking with the other class that I teach for CHEM103, and they wanted to have a take-home final where I'd post it and give you a week to work on it, and then you have to submit your answers on Blackboard by the end of the window that we have for final exam. So that would look like this. Your final is on December 8th from 2 to 4 p.m. I would post the final as a take home on December 1st. And then you post your answers like you did for exam 4 by 4 p.m. on December 8th. It's been a struggle semester. People have been getting sick, losing family members, all the things, okay? Believe me, instructors are not excluded. So, to make it a little bit easier for y'all, I normally allow you to make a cheat sheet and use that on the final, but I said, no, we need some extra grace today. So it will be a take-home final. You'll have a week to work on it and post your answers, okay? So I'm still working on grading your exam 4, but you will have that grade before you have your turkey meal. So don't worry, you will get your grade soon. Everything else is up to date. So if you have questions, you need anything, after office hours tomorrow, you can still send me a message, but we don't have class or anything next week. I'll send you messages via Blackboard so you know when we're doing office hours. But other than that, enjoy yourself, be safe. I hope your family has been safe thus far. And it's been a pleasure. It has really been a pleasure. So thank you guys, all 9 of us together. We ain't in strong in numbers, but that's all right. You're free to go. If you have any questions, this is a good time. Otherwise, happy Thanksgiving, y'all.